Hello and welcome to chemistry lesson 3.03, where we're going to talk about the mole. We're not referring to the cute little rodent with whiskers and little eyes. In chemistry, the mole is one of our most important base units. We just completed an activity where you guys created a unit and you used that unit to determine the amount of pieces of candy in a dish without counting the pieces of candy in a dish. And we started that activity off by me showing you a dish of copper and asking you how many atoms were in that dish of copper. And at the time, you could not solve that. But by the time we're done working with the mole, you'll see how chemists came up with this and are able to use it to calculate the number of particles or atoms or molecules in a given amount of mass. So to start with, let's put a definition down. So the mole is the SI base unit. And we talked about base units back in chapter 1. We talked about the kilogram, we talked about meter, and we said those are the base units. There's 7 base units. This is also a base unit, and this is the base unit for the amount of substance in a given amount of matter. Well, that kind of sounds like mass, right? Isn't that the same thing as mass? And in reality, it's not. When you come to physics, or if you come to physics, we'll talk a little bit more about what mass actually is, and it'll help you identify the difference between the mole and mass, but this is the definition. Well, what does that really mean? It turns out that the mole is similar to, we can think of this conceptually. It's like using a dozen or a ream. So if you think about it, a dozen is always 12 of something. You can have a dozen eggs, you can have a dozen ears of corn, you can have a dozen donuts. A ream is 500 of something. So if you have a ream of paper, you have 500 sheets of paper. Well, a mole is 6.02 times 10 to the 23rd of something. And that something is usually atoms or molecules. So the something is usually atoms, molecules, ions. And in this chapter, we're going to be doing atoms. Well, 6.02 times 10 to the 23rd is a really big number. In fact, it's so big that it's kind of hard for us to wrap our brains around. If I had 6.02 times 10 to the 23rd grains of rice, I would have more rice than has ever been grown in human history. If I had, if a computer was counting, so if I just, set a program and I told it to count, it would take, and you think about how fast a computer works. A computer works very quickly. It would take 25 million years for a computer to count to 6.02 times 10 to the 23rd. Let me say that again. It would take 25 million years for a computer to count that high. Well, isn't this a little, non-useful, having a number this big? Well, think about it. When we're talking about the number of atoms in a dish of copper, think about how small an atom is. An atom is really, really small, and it's going to be a really big number. And yet we need to know this very often. And so, yeah, we do need a unit that's going to have this size, that's going to have an exponent that's this large. This value, 6.02 times 10 to the 23rd, has a special name. It's called Avogadro's number. Avogadro's number. It wasn't discovered by Avogadro. It was discovered by someone else, and they named it for Avogadro because he had done a lot of work in determining how many particles were in gas. And so in his honor, they named it. And so what we did in lab was we ended up we took this conversion factor and we made it into what I like to call there's a swing. It could do two things. So let's just say one of the units we had was, so in our activity, we had shilly-shally. And on one side, a shilly-shally was equal to 10 M&Ms. And on the other side, we saw that the shilly-shally was equal to 12 grams of M&Ms. So this was our unit, and we kind of made it up. Well, in fact, we did. So on one side, we had number of pieces, and on this side, we had mass. And the shilly-shally was really kind of, even though it was fictional, what it allowed us to do was to convert between a number of pieces and mass. And we could take a dish if we had a mass and we can determine how many pieces it was going to be without ever counting them. So this is a conversion trick. In a sense, you can think of this as a conversion trick. Well, we do the exact same thing, but we do it now with a mole. So on one side, we have the mole, or in the middle, we have a mole of a substance. And on one side, we have a count. And the count is 6.02 times 10 to the 23rd. It's Avogadro's number. On the other side, we have a mass, and we call this our molar mass. So this allows us to do the exact same thing that we did in the activity, except if we needed to, we could have counted out those M&Ms. Can we count out 6.02 times 10 to the 23rd atoms? No, we can't. Well, let's talk about molar mass then. So we've got molar mass. Molar mass is defined as the grams in 1 mole of a substance. And this is kind of where the whole definition of a mole came in, because scientists said, let's make a mole equal to the amount of particles in 12 grams of carbon-12. Well, this is what that did for them. By saying we're going to make, so the mass of carbon-12 is 12 grams, and this is in atomic mass units. Atomic mass units. So what this did was this said that 1 mole, I'll write it here, 1 mole of carbon-12 is equal to 6.02 times 10 to the 23rd atoms of carbon-12, and on this side it is equal to 12 grams of carbon per 1 mole. So they kind of standardized it by saying this, by making this their base. We can now say that the Avogadro's number in 1 mole is equal to, and hopefully you recognize that this is the atomic mass. So what we're going to need to do, and the reason we spent so much time in chapter 1 going over conversions, is here we are, we're back at conversions. So what do I do about these conversion factors? I want to write conversion factor. Give myself a little more space here. When you write these conversion factors, so if I wanted to write these out in conversion factor form, I would write that 1 mole of carbon is equal to 6.02 times 10 to the 23rd atoms of carbon. And just like all of our other conversion factors, these could be flipped. So I could also write 6.02 times 10 to the 23rd atoms carbon in 1 mole of carbon. Then I have this conversion factor. I have mole to mass. So these two were atom to mole. I can also write mole to mass. So I can say that 12 grams of carbon are in 1 mole of carbon. By the way, the abbreviation is MOL. Or I could write 1 mole of carbon is 12 grams for carbon. Let me tell you right off the bat, the best thing you can do for yourself is memorize these. Understand that there's Avogadro's number in 1 mole and that 1 mole has 12 grams. What I'll see on tests is people will write 12 grams of carbon in 6.02 times 10 to the 23rd atoms. That is as wrong can be, and it will mess you up every time. You have got to get down that we have the unit here. In fact, the unit for molar mass is grams per mole. So we write that as grams per mole, and you can see here grams per mole. Well, what about this? This was just a flip. So we're just remembering that we can flip conversion factors. I just want to remind you of that. And again, in this chapter, everything we're doing is going to be atoms. So we're working with the mole on an atom level. What we're going to do in the next lesson is how do we use this to actually convert? So if I have that dish of copper and I get a mass for it, how can I calculate how many atoms are in it? And we're going to do this the exact same way that we did in the activity where we worked with candy. So this is our introduction to the mole. Our takeaways here is that the main one, let me switch colors. Purple. Takeaway number 1 is the mole is a swing unit. It lets us swing between mass and count. So on this side I have count, on this side I have mass. The mole really doesn't do anything for me, but it lets me convert between. Takeaway number 2, in order to do that, I have to write out conversion factors, and they have to be written out correctly. And we'll look in the next video, how do we use that? By the way, as a parting comment, why mole? Why M-O-L-E? That's short for the German molecule, which I believe is German for molecule. And so that's why M-O-L-E ended up coming into being. All right, that's our introductory lesson on mole. Thanks for watching and have a good day.